Good morning, everyone. We are here to present our topic rate Monotonic scheduling, one of the most fundamental algorithms used in real-time operating systems. I am Prakash Ganta, and with me are Vishesh Jabak and G. Vishal. Together, we will walk you through with what RMS is, how it works, and why it's still so important in today's computing systems. Let's start with basics. A real-time system is one where tasks must complete with a specific time limit or deadline. These systems are used in a place like medical devices, aircraft controls, or industrial automations where even a small delay can cause failure. In such cases, the scheduling algorithm plays a critical role in deciding which tasks run when. Scheduling simply means deciding the order in which tasks execute on the CPU. In real-time systems, scheduling isn't about fairness, it's about meeting deadlines. The algorithm must ensure that all critical tasks finish on time, even if it means lower priority tasks are delayed. There are two main categories: static scheduling, where priorities are fixed before execution, dynamic scheduling, where can change at runtime. Rate monotonic scheduling or RMS belongs to the static category. It assigns fixed priorities based on the task's frequency. Let's talk about rate monotonic scheduling itself. RMS is a primitive scheduling algorithm for periodic tasks. It assigns higher priority to tasks that need to run more frequently. In other words, the shorter the period, the higher the priority, to ensure the critical high frequency tasks to get the CPU time they need. Imagine two tasks. Task A runs every 10 milliseconds and task B runs every 20 milliseconds. According to RMS, task A will get high priority since it has a short period. Whenever both tasks are ready, task A will preempt task B. RMS makes some key assumptions for its model to hold true. Tasks are periodic and independent. Each task deadline equals its period. Context switching time is negligible. Priorities are assigned statically. If any of these assumptions fail, the algorithm might not guarantee deadline. The feasibility of RMS can be checked using utilization bonds for n tasks. The CPU utilization must be less than or equal to the given formula here. If the total utilization is below the threshold, all deadlines will be met. This formula is key to testing scheduling in RMS.
Let's take an example. Suppose task 1 has a period of 4 millisecond and execution time of 1 millisecond, and task 2 has a period of 8 millisecond and execution time of 2 millisecond. The total utilization becomes half or 50%. Since this is less than the bound of around 83% for two tasks, both can meet their deadlines. In RMS, priority depends entirely on the rate of recurrence, not an execution time or importance. This means a small, frequent task might preempt a long but less frequent one. The beauty of RMS is in its simplicity. The rule is clear and predictable. Here you can see a timeline diagram showing how tasks are scheduled. High priority tasks interrupt lower one whenever they are ready to run. The timeline clearly demonstrates preemption points, helping visualize CPU behavior under RMS. Whenever a high priority task becomes ready, it immediately preempts the lower priority task. This guarantees the faster task gets their share of CPU first. Of course, too much preemption can increase overhead. That's one limitation we'll discuss later. A common comparison is between RMS and EDF. While RMS uses fixed priorities, EDF uses dynamic priorities. EDF is more flexible and can achieve full CPU utilization, but RMS is easier to implement and analyze. RMS schedulability can be tested mathematically using the utilization test we discussed. For three tasks, the upper bound is around 78%. If your total utilization exceeds this, you might miss deadlines. RMS is widely used because it's simple, predictable, and efficient for periodic tasks. Its static priority model means designers can easily verify behavior offline. That's why it's still common in embedded, and safety critical systems. RMS forms the backbone of scheduling in many RTOS kernels like VWorks or FreeRTOS. It uses an automotive system, robotics, and process control where time reliability matters more than flexibility.
Despite its strengths, RMS isn't perfect. It assumes all tasks are periodic and independent, which isn't always true. It also doesn't handle tasks with varying deadlines or sporadic behavior well. And when system load is high, some tasks may still miss deadlines. Under overload conditions, RMS can fail to meet deadlines for low priority tasks. To counter this, our designers use techniques like priority ceiling or rate control to ensure critical tasks still run on time. Compared to other static algorithms like deadline monotonic scheduling, RMS is simpler but less optimal for certain deadline variations. Still, it remains the baseline for evaluating other scheduling methods. Here we present a simulation or case study showing how RMS performs under different loads. The results typically confirm that up to around 70 to 80% CPU utilization, RMS can guarantee all deadlines. Beyond that, the system starts to fail predictably. This graph visually represents CPU utilization versus the number of schedulable tasks. It is clear indicator of how utilization bounds decrease as task count increases. It also helps explain why RMS is best for systems with fewer well-defined periodic tasks. There are several improvements over RMS, such as deadline monitoring scheduling and mixed criticality scheduling. These variations adapt RMS principles to handle modern, complex real time needs. To summarize, rate monotonic scheduling is simple, predictable, and foundational. It may not be perfect, but it provides a strong base for understanding how real time systems ensure timing precision. It balances theoretical clarity with practical usefulness. That's why it's still taught and used today. That brings us to the end of our presentation on rate monotonic scheduling, RMS. We hope this session helped you understand not just what RMS is, but how it's applied in real systems. Thank you for listening, and we'll be happy to take any questions.